All right, guys. So we're going to go through the review for exam 4 here on power series and functions. And so there may be a slight correction to make in notation. I can't remember. And this version, it had P. So that should be T. A long time ago, the textbook we were using used P for polynomial, but most people use T for Taylor polynomial, of course. And then this one, sometimes I call T of X. So we'll probably use that throughout this review. All right, and then the other things are, standard Taylor series. I didn't give you all of them because you usually don't need all of them, right? Because some of them we may derive on the final. And of course, you have the binomial theorem here. And I can't remember, you might want to change that P to a K. There used to be a P up there, but I changed it to K. It just makes it's a better flow for all the material. All right, so we're going to go through this review, but real quick, before we get down to the sort of nitty gritty down here, right, to the details, remember the big idea of what we're trying to do. So basically, the big idea is if you give me a function f of x, these functions tend to look different, right? So you have this function f of x, and we have lots of different ways to write down functions, right? Sometimes it looks like sine of x. Sometimes it looks like e to the x. Sometimes it looks like a combination of these two. You can put these two together. You could just add them if you wanted to, e to the x plus sine of x. And they all look a little bit different. But the big idea that we discovered a couple hundred years ago, basically, what we discovered is that these functions, which are tools to do things, right? They actually help us compute things. So if you want to build some sort of building, or you want to understand how some sort of technology is operating, like or some sort of like physical phenomenon like electricity or magnetism, how it actually works and how to model it, we pull these functions and put them together to do that. And like I said, they often look very different. So when I look at these things, they don't look the same. They look a little bit different, but it turns out, right? It turns out they are all able to be represented by power series. So at the end of the day, they all have some sort of power series representation. So remember what that power series representation idea is. It's just this infinite sum from 0 to infinity. You have c sub n times x to the n, and that's centered at 0. But they have these sort of representations, sort of like the DNA of the function. And when you find this Taylor series, this power series for a particular function, we call it its Taylor series. So it's got a special name. And I honestly wish we didn't call it Taylor series, because Taylor's named after somebody, which is sort of silly because the Taylor has nothing to do with what a power series representation is. So, in my head, it's like, oh, you just get this power series representation of the function. And so what that means is if you find that power series like this, and we'll call it T of X, then you can graph T of X. This one's centered at 0. And what it'll look like is on some sort of interval, right? Some sort of interval here, going up R and down R, that power series T of X will be the same as the function. And so on that interval, you may need to include the endpoints, you may not. It's kind of, you got to test them, right? But that's the idea. You find that sort of power series representation, we call it the Taylor series, and it's equal to that function on some sort of interval there. Maybe I should have drawn this down a little bit more, right? So here's the function here, and then the blue power series or Taylor series is equal to it on that interval. And that's a big idea. All right, so it's kind of nice. It gives us a way to treat these sort of tools right here in a uniform sort of manner. We can then compare and contrast them to see how they're related to each other. And then you can actually use that technology to do computations. Like, I mean, think about it. If you know e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 and you want to find e to the 2, how the heck could you do that? Well, you can just plug in 2 wherever you see an x, right? So 2 squared over 2 factorial plus 2 cubed over 3 factorial plus dot, dot, dot. Now, you don't want to do this by hand. So what we do is we create a piece of technology, a piece of software, basically, that it can do this, and we can cut it off, right? We could go up to like 2 to the 100, if you want, over 100 factorial. And we could just compute it up to there. And this would probably be precise to like 10 decimal places. And that, who cares after 10 decimal places if you're using it, right? If you're using it, it's like, it turns out there comes a certain point where you can't actually determine equality, right? Because the universe, or this is called Heisenberg's uncertainty principle, right? So the universe determines, like, there's a cutoff point where you can't make any measurement more precise than it already is. There's always an error built in to the tool that you're using to make that measurement. So once you get up to a certain number, it really doesn't matter anymore, right? There's a bunch of stuff over here, but this is so small, it doesn't matter from a practicality point of view. And that's the idea. So it's a super powerful tool if you have some machine that can compute squares and cubes and stuff, and you can create machines that do that. Of course, you have a calculator that does it for you, basically. But that's sort of the power that power series give to us, besides understanding the relationships between other functions. All right, so let's get into this review. So that's the big idea. Now let's just do the sort of technical, the technical parts here. So we're just going to go right through this. And so we're going to start in order of how we covered the material. So here's a power series. Let's give it a name. We'll call it P of, actually, I guess I called these S of X probably for series, because I was calling the series S. So S of X equal to this, right? The sum n equals 1 to infinity, 1 over n times 2 to the n, all times x plus 5 to the n. We want to find the radius of convergence and the interval of convergence. So how do we do that? So let's just write a few things down here. So for the radius of convergence, the idea is that this thing is centered at 5. So at the back of my head, and it's not 5, it's actually minus 5, right? So it's x minus a negative 5 here. So this is actually centered at negative 5. And I want to figure out how far can I go out here, negative 5 plus what versus negative 5 minus what, that I can guarantee convergence on that interval. Notice it's very clear it converges at negative 5, because if you plug in negative 5 here, you get out 0. So it's very clear, a center point that it's going to converge. And then the question is, how far can you go out on either side and still get convergence? So what we're going to do is we're going to use that ratio test to help us figure that out. So remember what the ratio test says. It says you basically just take a limit as n goes to infinity of the absolute value, and you take the next term, so a sub n plus 1, and divide by the term before it. And it's basically like a test for seeing how geometric your series is, right? Because if you know it acts geometrically in the end, then if that r you get out, that limit is less than 1, it converges, bigger than 1, it diverges, equal to 1, inconclusive. We're not quite sure. And so what's our a sub n right here? So let's make this very clear. This is our a sub n. It's just the term. So a sub n is equal to 1 over n times 2 to the n, and then don't forget that x plus 5 to the nth power. And so now that I know what my terms are, I just basically kind of plug it in and run the limit on it. So the limit as n goes to infinity, absolute value 1 over, and then wherever you see an n, you're going to replace it with n plus 1. Right? So it's going to be 1 divided by, and I have n plus 1 on the bottom, in parentheses, 2 to the n plus 1. And if you want to put that in parentheses, you can, it's okay. And then up here, I have x plus 5. And then again, wherever you see an n, I'm just replacing it with n plus 1. So n plus 1. And then all divided by, and then on the bottom, I just have this a sub n. So you just copy this down basically. And so that's 1 over n, 2 to the n times x plus 5 to the nth power. And then don't forget to close off your absolute value there. So that would be my first step. after I write down what to do, right? Just read it and do what it says. Now I look at this thing and I want to simplify it. So I'm basically going to multiply it by its reciprocal. I'll kind of clean it up as I go because you kind of know what's going to happen now. So it's like the limit as n goes to infinity. I have basically 1 over n plus 1 in parentheses. This 2 to the n plus 1, I'm going to write that as 2 to the n times 2 because I know those 2 to the n's are probably going to cancel. And then on top here, I have an x plus 5. So I'm going to actually just write a parenthesis here and put x plus 5 to the nth power times another x plus 5. So I can separate those because, again, I know those are going to somehow cancel with that bottom part. And then times, and then I'll do this one in red. I'm just going to take this and I multiply by the reciprocal, right? Because when you divide by a fraction, you multiply by the reciprocal. And so here I do n times 2 to the n divided by, and then it's x plus 5 to the nth power. And then again, don't forget, you still have absolute value on this thing because x's could be positive or negative, or x plus 5 can be positive or negative. You need to keep those absolute values on there. And so now x plus 5 to the n is going to cancel with x plus 5 to the n. 2 to the n is going to cancel with 2 to the n. And so this is going to equal, if we just copy it down, the limit as n goes to infinity, and then I have absolute value of x plus 5 on top divided by, and on bottom, it looks like, oh, and I have an n over here too, so times n. And on bottom, I have an n plus 1 times 2. So let's make sure I didn't miss anything. So I have an x plus 5 and an n plus 1 times 2. Looks good. So that's what happens when I simplify. And now I can use properties of absolute values. Remember, absolute value goes through multiplication and division. It does not go through addition and subtraction. So very careful. Right? Remember, like if you have absolute value of 1 minus 2, that is certainly not equal to absolute value of 1 minus absolute value of 2. Right? This answer is 1, and this answer over here would be negative 1. So that's not a true statement. But if you have absolute value of 1 times negative 2, it does turn out it goes through multiplication, absolute value 1 times absolute value negative 2. Those are both positive 2 on both sides. So it goes through multiplication, and it does the same with division. So when I think about that, I'm like, okay, well, I'm just going to pass this absolute value through everything. If it's positive, I'll drop it off. If it could be negative, I'll leave it alone. So this turns out to be the limit as n goes to infinity. The absolute value of this has to stay. So I'll put that over here, absolute value of x plus 5. But the absolute value of n is just n divided by absolute value of 2n plus 1 of n plus 1, I'm sorry, is just n plus 1. And absolute value of 2 is just 2. So that's really 2n plus 2 on the bottom. And the reason I multiplied through is I want to make it very clear what this limit will be. So this will be equal to, so when you run the limit on here, the only thing that changes is this. This is a constant with respect to the limit. So this is an n over 2n basically. So it's going to be a 1/2 times that absolute value of x plus 5. Right? And that's because you have an n on top and a 2n on the bottom. So it's basically, as you go to infinity, it's linear on top and linear on the bottom. So it goes in the same way, basically as a 1 over 2. So 1/2. All right. So there's the limit. And so now what can I say? I want to say, therefore, s of x, that way I don't have to write it all down, I give it a name, s of x converges for 1/2 absolute value of x plus 5 less than 1, which implies absolute value of x plus 5 is less than 2, right? You multiply both sides by 2 basically here, which implies r is equal to 2 by the ratio test. And so remember, this idea right here is captured right up here. So this is just saying you have a center point. If it's x plus 5, that means it's x minus a negative 5. And it's telling me if you go out 2, you have to kind of stop. So negative 5 plus 2 is negative 3. And if you go to the left 2, so -5 minus 2 is -7. And so I know on this interval so far, I get convergence. And then the question becomes, what happens at the endpoints? So to find the interval of convergence, I need to test those endpoints here. So let me zoom out just a little bit and move it over. And now we can test those endpoints. So for the endpoints, we have what? We have s of -7 to test, and we have s of -3 to test, because those are the endpoints on my interval. And so what's s of -7? Well, you come up here, you erase some stuff up here. You come back up here to your original series and just do what it says. So if we line it up, write it up right, you just do what it says basically. And so we're going to plug a -7 right into here for x. So we get the sum, and don't forget the sum. That's important. Without the sum, it's not a series, it's a sequence. We want the series. So sum of n equal 1 to infinity is 1 over n, 2 to the n. And something special should usually happen when you plug in -7. So notice, if you plug in -7, -7 plus 5 is -2 to the n. And so hopefully when you look at that, like, oh yeah, something special is happening. I got 2 to the n on top and a 2 to the n on the bottom. So something's going to cancel basically. So this is going to be the equal to the sum. And we're going to go slow here. So remember, -2 to the n is really, so maybe over here we'll write this. So -2 to the n, this is me just sort of thinking to show you, is really -1 times 2 to the n. Which remember, you can bring through exponents through multiplication. So it's -1 to the n times 2 to the n. And so here I'd write this as -1 to the n times 2 to the n on top. And on bottom, I have n to the 2 to the n. And I see very clearly the 2 to the n's are going to cancel. Oh yeah, I get this alternating series now, which is one we've seen a lot of. This is the alternating harmonic series, but it definitely converges by the alternating series test. So converges by alternating series test. All right. So what does that mean? That means in my picture on -7, you're going to include that endpoint. So I'll put a square bracket on my little picture up there because I'm going to include that endpoint. And then I got one more to do. So I want to do s of -3. So I'm going to plug -3 in here for my x, right? So let's do it in blue. So -3. So I'll plug -3 in for my x there. And so I get the sum, n equals 1 to infinity, of 1 over n, 2 to the n, and then you're going to get the other side. So you have -3 plus 5, which is times 2 to the n. This one's even easier because these cancel right away. And so I get the sum, n equals 1 to infinity, of 1 over n, which we know diverges because it is a p-series with p equal to 1, which of course is less than or equal to 1. Which means up here on my picture, I'm going to keep that a parenthesis. So therefore, what do I know? Therefore, s of x converges on what? -7 with a square bracket on it, up to 3. I'm just looking at my picture here. I drew down there, up to 3 with a parenthesis, and that's it. Here's my interval of convergence, right? So radius of convergence was 2. Interval of convergence was -7, comma 3. And so what's interesting about this really from a research perspective is basically if you discover some sort of weird sequence, you can always take that sequence, whatever it is, C sub n, and turn it into a power function, and then ask yourself, what does that power function do? Because it represents some sort of function. It's almost like, you know, finding some sort of new way to combine DNA, and it's like, it should give us something. What kind of thing would it give us, you know? And so that's kind of the interesting part about power series. You may not know what type of function it is, but you can always write it down. And sometimes you might be able to figure out, is it an elementary function or not? Or maybe it's something new, something a little bit more interesting. Okay, so we have one more of these types of problems to do, but it's just finding the radius of convergence. All right, so let's look at this one here. So here's my power series S of x equal to the sum and equal 1 to infinity of n factorial over n squared times x to the n. Now, I will tell you, we've been doing enough of these that I know this factorial grows much faster than the square. So basically what's going to happen is that this is probably not going to converge for much of anything, because the coefficient in front of the x to the n's is just going to grow so quickly that it's going to probably knock everything out. But let's just show that. So this is an example probably where the radius of convergence is 0. But let's just see what happens. So what's the idea? How do we find that radius of convergence? Well, I'm going to use the ratio test. Right, this will tell me where this thing is going to converge and diverge. And so for the ratio test, I have to identify my a sub n's. So my terms are just the n factorial over n squared times x to the n. And so I'm going to look to see if this is going to behave, or when does it behave, basically geometrically. So I take the absolute value of a sub n plus 1, the next term over the previous term, and see what kind of thing I get out. So the limit as n goes to infinity. And what do we have here? So I just kind of read it and do what it says. So it says basically you have absolute value and you put a sub n plus 1 on top. So wherever you see an n, I'm going to color them in blue, you're going to rewrite an n plus 1. And if you want to help yourself, if you have problems with this, just put it in parentheses. So n plus 1 in parentheses all the way around. So here I'd have n plus 1 in parentheses and then put a factorial on it. On the bottom, I'd have n plus 1 in parentheses, and I put a square on it. And then I have an x to the, and just for fun, just so you can see that idea of putting parentheses on it, it still works, right? You don't actually need parentheses on the top part there, but you can just leave it. And we'll drop them off in a minute. And then this is going to be divided by, so divided by what? Divided by a sub n. And so that you just copy down. And so that's n factorial over n squared times x to the n. And of course, that's all inside an absolute value. And so that's my first step. My next step is I want to show how things are going to cancel. So to show how things are going to cancel here, I'm going to get the limit as n goes to infinity. And I kind of know a couple things like n plus 1 factorial and n factorials are going to somehow cancel. So I'm going to write that n plus 1 factorial as n plus 1 times n factorial. And then this x to the n plus 1, I know it's going to basically cancel with that x to the n. So I'm going to write that as x to the n times another x, because exponents add here, right? If you want to put a 1, you can. And then divided by n plus 1 squared. And then times what? So times, and then I'm going to multiply by the reciprocal of this. So notice the x to the n, remember, is on top. If you want to extend that quotient there, you can. And so I hit n squared on top, and then n factorial and x to the n on the bottom. And then again, don't forget, it's all in absolute value. And so I see now the n factorials are going to cancel. I see now the x to the n's are going to cancel. And so what am I going to get? This is going to be equal to the limit as n goes to infinity. And I have an absolute value of x, that's got to stay. So absolute value of x. And then I have n squared on top. I don't need absolute values on it because it's already positive, because n's going to infinity, but if you square anything, it's still positive. And on the bottom, I'm dividing by n plus 1 quantity squared. So I'm going to write that as n squared plus 2n plus 1. I'm going to multiply it out just so you can see when I take the limit, it's very clear what I'm going to get on here. All right. Okay. All right. So I stopped. I paused. Let me tell you why I paused. Because when I take this limit, I felt like, oh, it's going to be a problem because that's a 1. If that's a 1, I know I did something wrong because I don't want to get a 1 there really. And I did that because I forgot what? I forgot that n plus 1. Do you guys see that? I just didn't see it. All right. So let's fix this. Let me fix it real fast because that cancels too, right? So that makes this problem a little bit easier. So this n plus 1 cancels with one of those n plus 1s right there. And so on bottom, I just have a single n plus 1. Now I'm happy because, again, intuitively, I know this is going to blow up. So this whole thing is going to go to infinity. So it's going to be equal to, when you take the limit, all I care about is this piece here. This is a constant. So I have the absolute value of x, that just stays there, times, now what's this limit? Well, the power is bigger on top, the degree is bigger on top. So it's going to go to infinity, right? So it's n squared on top and on the bottom. If you want to L'Hopital it, you can, but basically if the degree is bigger on top than the bottom, the top's going to dominate and force it up to infinity. And so that's just equal to infinity. Which, of course, infinity is always what? It's always bigger than 1. Therefore, S of x converges for just x equal to 0. All right, the only time this actually doesn't equal to infinity is when, I mean, I guess we should, it's greater than 1 as long as, you don't have to write this. I mean, x is not equal to 0. Because what happens when x is equal to 0? Well, you're multiplying by 0, it turns out. Right, so it'll wind up being 0 before you take the limit, because when x equals 0, guys, you're going all the way back here and letting x equal 0. So as soon as you plug it in, everything's 0 basically. So nothing works out for you. It's just, 0 basically. All right, so, and this is by, and so this implies, so let me put implies, the radius is equal to 0. Right, so what you're saying here is basically, you're trying to find that radius. It's 0 plus r, because it's centered at 0, 0 minus r. You found that the radius was 0, so it just converges at the input 0. And this is by the ratio test. And I'll put this in parentheses because you don't need to put that there. All right, so I wanted to do an example where the radius wasn't an actual number or it wasn't infinite. It turns out this is only converges at one singular point, which means it doesn't really give you much information whatsoever, right? I mean, this whole function is basically 0. Nothing happens around it. It's like a DNA sequence that doesn't represent anything, basically. Okay, so that concludes sort of power series stuff. Now let's go on to Taylor polynomials. All right, so let's talk about these things here. So remember, you are going to get the formula. So let me go back here and we'll cut the formula out for you guys so you can see it. I got to snip it. So let's snip it here. So on the exam, you'll be given this formula and you just have to know how to use it, basically, do what it says. So it's kind of a nice little problem in the sense that you're just learning how to use a formula, right? And most of you guys know kind of how to do it, but we just got to do it correctly. Okay, so what do we want to do? We want to find the third degree Taylor polynomial centered at that number a and make sure to include a table. So there are a number of ways to do this. I would just start out, since I'm reviewing here with you guys, I just said, let's just do what it says. You want to find the third degree Taylor polynomial. So n is 3. And so let's just do this up to 3, right? Which is just this piece right here, basically. So we're going to do, this is going to be f of, and we're centered at pi over 4. So f of pi over 4 plus, and then f prime of pi over 4 times x minus pi over 4. And then I'm going to get this out of my way here. Then plus f double prime of pi over 4 divided by 2 factorial, which is just 2. So then x minus pi over 4 squared. And then I'm not done because that's the second degree Taylor polynomial because it's squared. I need one more. So I'll do f. I'll put a little 3 here. You can do triple prime if you want of pi over 4. And then 3 factorial is 6. 3 times 2 times 1. And then x minus pi over 4 quantity cubed. So that's what I need to find. And when I write that down, it tells me basically what to do. It says basically find the function at pi over 4, find the derivative at pi over 4, find the second derivative at pi over 4, and find the third derivative at pi over 4. So once I write it down, it's now telling me what I need to do. And it does say make a table. So I'm going to make a table here. So let's make it right here. And that table, I have n. And n is going to be 0, 1, 2, and 3. And I'm going to find the nth derivative of this thing. So we write little parenthesis n of x. And then I'm going to evaluate it at pi over 4. And I may need to move this over a little bit. So I'm going to eventually evaluate this thing at pi over 4. And once I get those answers, I can simply just come back here and plug in to what I have there. All right, so that's my game plan. All right, so what's the original function? It's tan of x. So when you plug a 0 in there, it means no derivative. And so you just get the function back, which is tan of x. So we start with tan of x. And then we got to take a derivative of tan of x. Well, remember, what's the derivative of tan of x? Well, that's secant squared x. So we can't forget our derivatives, which is really, because I'm going to take a derivative of that. So remember, that's really secant of x quantity squared. And so I'm going to write it like that because I want to take a derivative of that. So the next derivative, the 2 is going to come down. So I get 2 times secant x. Oops. And then times, don't forget, you have to multiply it by the derivative of its inside. So here's its inside. And the derivative of secant x is secant x tan x. And so this is going to be equal to 2 times secant squared x tan x. And I wish I was done, but I'm not. I got to do it one more time. So let's do this one more time. And so to take a derivative of this, you got to use a product rule. You basically have a first function and a second function. So the next derivative, the 2 is going to pop down on that 2, and you get 4 secant x times the derivative of its inside, which again is secant x tan x. So that's the derivative of the first times the second. So times the tan x. And it's a product rule, so then it's plus the first function, so 2 secant squared x, and then times the derivative of tan of x, which is secant squared x. All right, so that's a monster in itself. And so then what is that equal to? So that's equal to 4 secant squared x times tan squared x plus a 2 secant to the 4th x. What a mess, right? But not so bad. I mean, once you get it right down. And hopefully for some of you guys, when you watch this video, or the guys that are here with me, when I do this, hopefully you realize like the issue with trying to write out the rule versus trying to listen to the saying and doing it, right? So there's always this issue. If you try to include too many steps and write things out, like identify f and g, f prime, you have to kind of look at this and identify, let your brain identify and speak, say, oh, here's my first function, here's my second function. Remember the rule, the derivative of the first, there that is, times the second, plus the first, times the derivative of the second. So I put a little prime up there. And so my brain, you say it, and as you say it, it'll start to unwind and do it. I don't know if you guys, we have lots to say, like lefty loosey, righty tighty. It's kind of like your brain likes to do stuff like that. It likes a saying, like you say it, and it'll follow the directions as you do it. This is also encoded in numbers I found over the years. Like if I just write down a number and you look at it, it might be a little bit harder to remember. But if you say it out loud, 32,567, and then you pause and you write it down, that saying, like it echoes in your brain. Like it's echoing around. And so it's still in there. As it echoes, you can then recall that information as it's kind of echoing in there and write it down usually. So it's kind of like there's some sort of procedure there, I feel like, that we're using, that we've evolved. Okay, so what do we have to do next? Next, we got to plug in that pi over 4, man. So it helps since we're plugging in here. So what's tan of pi over 4? And this is a little bit tricky, right? Because you have to kind of think, oh, what's tan of pi over 4? Well, it's sine of pi over 4 over cosine of pi over 4. Remember, those are exactly the same, root 2 over 2. So that's going to be 1 over 1. So in my head, I'm like, oh, it's like 1 over 1, which is 1. So that's nice. Whenever we do tan of pi over 4, it's going to be 1. And then we have to plug pi over 4 down here. So we need secant of pi over 4. And we're going to square it. And so what is that going to be equal to? Now here, I have to think a little bit more. So a secant of pi over 4 is really 1 over cosine of pi over 4, because I really only know things in terms of sines and cosines. And then remember, cosine of pi over 4, I know that one. It's 1 over root 2 over 2. And then I'm going to square it. So it's really, I'll multiply by the reciprocal, 2 over root 2, and I'm going to square it. And so that's equal to 4 over 2, because you square the top and square the bottom. And of course, you get back 2. Now that I know what tan of pi over 4 and secant of pi over 4 are, I can just use that on the rest of these. So notice on this one down here, I'm going to plug pi over 4 into here, and I'll write out what I'm doing. So secant of pi over 4, and I'm going to square it. And then times tan of pi over 4. And so that's going to be equal to, well, we just found this. This, when you square it, is 2. So we get this equal to 2 times 2. And this we just found was 1. So that's going to be equal to 4. And then down here, I'm going to plug it in again. So this is going to be 4. I'm going to show my work so you guys can see what I'm thinking. I have secant of pi over 4, and I'm squaring it. So I square this. And then I have tan of pi over 4, and I'm squaring that too. And then plus, I have 2, and then secant of pi over 4, and I'm raising that to the 4th power. And so let's see, what is that going to be equal to? So I have 4 times, again, we just did this. That was the number 2. We just did tan of pi over 4, which is 1. And so you have 1 squared. Plus I have 2 times, now here's where it's a little bit tricky. This is to the 4th power. So it's like secant pi over 4 squared, and then you're squaring it. So you take 2 and you're going to square it. And so then that's equal to an 8, because 4 times 2 is 8, plus a 2 times 2 times 2 is 8. And so we get back 16. And so now, all that work, what do I do with it? So let's let me show you what you do with it. So we're gonna come back here. Let me zoom out a little bit. We'll scoot over a little bit. And so we're gonna take all those numbers and just plug them in. So this will be equal to, what was f of pi over 4? Well, it was 1. So it's equal to a 1 plus What was f prime of pi over 4? Well, that was a 2. So plus 2 x minus pi over 4 plus what was f double prime of pi over 4? Well, that's down here. That's the next one. That's a 4. And so plus 4 over 2 times x minus pi over 4 squared. And then finally, plus 16 was the third derivative. So I have right here 16 over 6 times x minus pi over 4 cubed. And so then finally, this is going to be equal to 1 plus 2. I can simplify it just a little bit. You could have done this above, but I'm just really want to show my work on this video for you guys. So 4 divided by 2 is 2. X minus pi over 4 squared. And then plus, this reduces to what, 8 over 3? The 2's cancel, so 8 over 3, x minus pi over 4, quantity cubed. So that's got a lot of great stuff in it for you guys. All right, and then remember, if you ever have trouble with derivatives, you need to remember how to do them. You can go back. I have a whole sequence of Calc 1 videos. You know, I do a flipped Calc 1 class. So you can go through those videos. If you think your derivatives are weak over the break, you guys can, you know, learn better how to take derivatives. I always, you know, I don't think I told your class this, but I always tell like my lower level classes, college algebra and like pre-calc, like nobody does this stuff over the break. It's like, you know, you're wanting to be a professional athlete, but for some reason, all your peers decide not to practice over break. So if you just practice over break, you always get like a 1-up the next semester, basically. Okay, so that's Taylor polynomials. And now we move on to what we did at the start of here is, you know, determining which series to use, right? So to do this, remember how this worked actually. This was bids, right? So we did BIDDS just to identify which was which. The binomial theorem worked because that has the right form. That's really a 1 plus x to the negative 1/2. So that was pretty easy to figure out. So binomial theorem was off of there. Substitution usually is pretty easy. And we had kind of two choices, remember. We had this choice or that choice. And it turns out we chose this one because this one we could use differentiation on. So we talked about how basically this looks like the derivative of 1 over 1 minus x squared. And I knew that because of that square there. I'm like, if I look at this one, 1 over 1 minus x, let me clean it up, squared to the -1, and I take a derivative of this, I'm going to get this back exactly. So it matches up. So that's differentiation. And then we talked about how these two, you could actually, so once we got differentiation gone, we can use either the definition, which is this d, or integration. And really, you could go either way on these, but we chose to do integration on this one because that's what we've been doing, and then use a definition on the one below it. But again, you could go either way. It actually wouldn't matter. So now what we want to do is take those methods and apply them one at a time. So let's do this. And we're centering these at 0. So we want to find the Taylor series, center at 0, and the interval of convergence for each of the functions above using the method listed. So let's just kind of go through these. So we'll do A. And so let me write down the function. So f of x is equal to 3 over 1 plus 2x. And so now remember, let me snip this back here. We have these two formulas that are given to us. So we're allowed to use these things right here and a binomial, right? So here, let's get that off there. So I'm going to carry this around with us. So we're allowed to use, and I guess we're actually allowed to use this formula here too. So let's bring that with us too. Okay, so let me put that right here. Make it a little smaller. That'll work. Put it right over here, I guess. Okay, so I'm gonna do substitution on this, and this one actually goes really fast. The idea is we know this is true. So we're given this piece of information. It's basically just a geometric type of series where r is now x, right? So all I have to do is make it look like that. So I need to make it look like a 1 divided by 1 minus something. So not just x, but something. And wherever you see that something, you replace it with what you have over here. So this is equal to, I'll take care of the 3 first. Again, I'm going to go nice and slow on these so you just really see my thought process. So that's my first step. Just put a 1 up there. That's my goal. How I get a 1, I can pull out the 3. Now I want to turn this plus into a minus. So that'd be equal to, and I'll write this as 3 times 1 over 1 minus, just write a minus there. And how do I get a plus 2x? Well, I'll put this in parentheses. I'll write a negative 2x. And now I got it. And so that was my goal. I knew my goal to write it in this form, in this shape, basically. I mean, it's a form, but to me, it's like kind of like a shape idea. Like manipulate it geometrically to make that shape, but we're manipulating it algebraically to get that form. And so what I can do now is just plug this in for that triangle and for that x, basically. So it's going to be equal to 3 times the sum n equals 0 to infinity. And wherever I see that triangle or that x, I replace it with negative 2x. So negative 2x in parentheses, right? So put that parentheses around it, and that's to the n. And that's for all. So here, I'm going to go down here. So 4. And then if you want, you can put those parentheses on it. Negative 2x is an element of negative 1 to 1. All right. So again, if you're struggling, just put parentheses around that thing you're substituting for, and you'll hopefully not make a silly mistake. And then you can drop those parentheses off once you feel very comfortable doing this. And so then this is equal to, now we have to clean it up. So when I raise that to the nth power, it's really what? So this is going to be 3 times the sum, n equals 0 to infinity, of negative 1 to the n times 2 to the n times x to the n. So I separate it all at once. So we did that before. So hopefully that makes sense why I can write it as negative 2 as negative 1 times 2 and then bring it through. And then this will work for what? So 4, I'll divide this by negative 2 on both sides, basically. And I get x is between. Now here you have to be a little bit careful. I know this is 1/2, but it flips the interval. So you write negative 1/2 over here and the positive half on the right. Remember, if you do it the other way around, it actually is incorrect. I don't need to put that on box yet. And I'm almost done. I don't want to leave that 3 on the outside, because remember, my end game is always to write this as a sum of c sub n to x to the n, because that is the Taylor series centered at 0. If you put a number on the outside, it's not really the Taylor series, because it should be the sum of something times x to the n if it's centered at 0. And so I'll rewrite this one last time as the sum, n equals 0 to infinity, of negative 1 to the n times 3 times 2 to the n times x to the n. And I will write on the same line for x an element of negative 1/2 to 1/2. And these are all parentheses. Remember, the interval really doesn't change unless you're doing integration, because integration makes things better sometimes. So sometimes you have to check those endpoints. We did talk about differentiation makes things worse, but we never have a problem that you have to check to make sure you don't include the endpoint if it is included before. Okay, so that looks good, right? So moving on to the next one. So part B. And so on this one, this is kind of the hard one, basically, because binomial theorems, I feel like it's one of the tough ones. I don't really like to do the binomial theorem. If I can avoid it, I will. So I have 1 over the square root of 1 plus x. Really, the only way to avoid the binomial theorem in this one is to use a definition. So they're kind of just as painful. So what I like to do is I just try to go slow, right? I know I'm allowed to use the formula, so I might pull the formula up here so I can kind of look at it as I go. But I just kind of try to go slow, and honestly, I don't really need the formula, but it does make me happy when I have it on the page. It's kind of like a calculator. I don't really need a calculator, but it's nice to have to check my work. So I'm going to rewrite this as the 1 plus x to the negative 1/2. That's very important, because if you don't get the exponent right, then everything that follows is wrong. But I see, that's the idea. So I'm going to use that binomial theorem. And again, I just like to go slow. So I'm like, okay, this would be the sum, n equals 0 to infinity. And I'd write this as -1/2, choose n. And that's then times x to the n. So that's this part of the formula. And then I actually like to write these out sometimes. I just feel like my brain needs the time to accept what I'm about to have to do. So it's like, oh God, I don't want to do that, but I will. All right, so -1/2, choose 0, -1/2, choose 1. But on an exam, I might skip this one just because I know I'm pressed for time. -1/2, choose 2. And I see the pattern, and so it makes me feel a little bit better. -1/2, choose 2, x squared plus ... And then I basically just do what it says. So -1/2, choose 0. Anything choose 0 is 1, which I mean, again, you can look at this, that's 1. And then plus, and then -1/2, choose 1 is just -1/2. So it's going to be -1/2. And again, I can look at this and just write down kx, so times x, plus -1/2, choose 1 is -1/2, and then -1/2. Oh, I already did that one. I'm sorry. My brain's doing like, what are you doing? Because I want to do choose 2 next, right? So let me, that negative's bothering me because I can't see it. So the negative right there. So -1/2, choose 2, I'm sorry, right, is -1/2. That's the first one. Then -1/2 minus 1 divided by 2 factorial. And that's x squared. And you're going to have to do a couple of these. So I'm going to do -1/2, choose 3. So it's -1/2, -1/2 minus 1, -1/2 minus 2. And my brain likes that. There's 3 things divided by 3 factorial, x cubed. And I'm even going to do one more just to hit it home. -1/2 times -1/2 minus 1. So I'm doing choose 4 now. And -1/2 minus 2. -1/2 minus 4, or minus 3, I'm sorry. And then all divided by 4 factorial, x to the 4th, plus ... Now that may be overkill, but that's okay with me. All right. And so there's the pattern. I see the pattern. I feel good about the pattern. Now I just got to simplify this just a little bit to see what's happening. So, and you don't want to simplify too much. So I'm going to leave this as a 1. That's a -1/2. So I keep that there, x. And then a minus times a minus will still be a plus. Now, I kind of put this together. So it's like that's -1/2 and that's -3/2. So what I have here is -1/2 times -3/2, which is a plus. And on top, I have a 1 times 3. And on the bottom here, I have a 2 times 2. So that's 2 squared. And I also have a times a 2 factorial on the bottom. Okay, and that's x squared. And I'm guessing it's going to be then, let's change color. So I'm guessing that it's probably going to go minus, but let's check it out. So I have a -1/2, a -3/2 here. And I bet this is a -5/2. So you're taking off 1 more from 3/2. So it's like -5/2. So yeah, it's definitely going to be negative. A negative times a negative times a negative is a negative. And on top, I'm going to have 1 times 3 times 5 divided by a 2 times a 2 times a 2. So 2 cubed. And then times 3 factorial, x cubed. And then plus, I bet at this point, if you had to, you could just guess at what the next term is going to be by following the pattern. If you can do that, you're ready to go to the next step, basically. So I think it's going to be a 1 times 3 times 5 times 7. I feel that that's how it's working on top. Divided by 2 cubed. I bet it's 2 to the 4th. And I bet it's 4 factorial times 4 factorial and x to the 4th. So hopefully you can kind of see the pattern. And then, of course, don't forget the plus ... to communicate, yes, this is going to go on forever and ever in that way. And I think I see most of it. So let me show you what I would probably write down. I'd probably write this down. Go back up just a little bit here. I'd probably write this down as being equal to, and I'm going to leave a space here, but I may not know I need a space in the beginning. So I'd probably write this down as a sum, n equals 0 to infinity, but I'm going to fix that in a minute. But it seems to me on the bottom, I always have this, I have x to the n right here. That's an easy part, right? X to the n. And I seem to have 2 to the n and then n factorial, because these are all lining up. I don't know if you guys see that. It's like, oh, they're all lining up. And then on top, I'm going to move this over a little bit in my more space. On top, it's alternating. So I have a -1 to the n. And then it's going 1 times 3 times 5 times 7, ... up to something, which I don't quite know yet. Move that over. Give myself more space. So I'll put a question mark here. So I got to figure out what I'm going up to, because I see the ending number, you know, like when it's 2, it's 3, when it's 3, it's 5, when it's 4, it's 7. So I got to figure out how that works. So maybe over here, I'll make that table, right? And so on my table, let's make it right here, I guess. So let's go in, and we're trying to find this little sequence here. So I have 0, 1, 2, 3, and 4. And notice for 0, I just have a 1. So I got to write a 1 there. On this one, for 1, I have a 1. But as I go up, I get some more information. So I have a 1 times 3 for 2. And I have a 1 times 3 times. I'm just actually write the end term because that's all I really care about, right? So here I have a 3, here I have a 5, and here I have a 7. All right, so I'm just carrying 3, 5, and 7. I'm looking for a formula, right? And I see the pattern. If you want, I could actually go a little bit further. I bet if I put a 5 here, I should get a 9. And I want to know what I do for n. And the problem, remember, is what? The problem is I have 2 1s here. So I'm going to have to cut that off somehow. And I think I could probably just cut off one of them, because it goes 1, 3, 5, 7, 9. So I think that would probably do it. All right, so I'm probably going to have to put that first term out here. So I'll have a 1 plus. That's that first term right there. And so then I'll have to start this at 1. That'll kind of change that business there. So start that at 1. But what's the formula? All right, so maybe you can look at it and say it's 2n minus 1, but maybe you can't. And if you can't, that's okay. You just know it's linear because each time you're adding 2. So each time you're adding 2, each time you're adding 2. So if you can look at that and tell me what's happening, I'm like, that's great. So if you want to be like, I know it's 2n plus or minus something, so I'm going to guess 2n minus 1. And you see that works, like when you plug in 5, 2 times 5 minus 1 is 9. Great. If you don't see that, though, remember, all you have to do is know the form. It's an plus b, right? It's linear. So if you want to mx plus b, that's fine too, but I just usually use a and b, the beginning letters of the alphabet, for when we do sequences like this. And so what does this say? It says, hey, when you plug in 1, you get out 1. So we know a plus b is equal to 1. When you plug in 2, you get out 3. So we know that a times 2 plus b is equal to 3. And then we can just take these two things to find a and b and solve. So we'll subtract the second equation from the first equation. So 2a minus a is a, plus b minus b is 0, and 3 minus 1 is 2. So a is 2. So now we know that 2 plus b is equal to 1. Well, that tells us what b is. So bring over 2, and b is equal to -1. Perfect. -1. Ugh. -1. So you subtract 2 from both sides. And that tells you what? A is 2n minus 1. Perfect. I can find that if I have to. If my brain gets stuck and I can't figure out how to move it forward, I can force it forward by using a little tool called a formula and solve those system of equations. All right, so what have I found? I'm going to come back up here. I'm going to erase my question mark, and I'm just going to write 2n minus 1 in parentheses. And that'll do it. And then don't forget, I forgot what? I forgot my interval of convergence. So way back here, I was so sort of in line with this. I should have written 4 x between -1 and 1. It's kind of focused on trying to solve the problem, right? So down here, I should write 4 x between -1 and 1. And again, you don't have to test endpoints. the endpoints, it should diverge. Okay, so that's kind of a tricky one, I always think. It looks good. All right, so moving on to C. So C is integration. So let's take a look at this one. So C. So our function is equal to ln of 2x. ln 2 plus x, I'm sorry. All right, so I could use the definition on this one, but we chose to do it on the next one. So I'm going to do integration on it. And so I got to figure out what function, when you integrate it, do you get that? So basically, I'm like, oh, I can do that. It's like the integral of 1 over 2 plus x dx. That'll work. All right, so when you integrate that, you basically get this ln of 2x, well, ln of 1 over 2x. Sorry, when you integrate that, you get ln of 2 plus x back, right? Because the derivative of ln of 2 plus x is 1 over 2 plus x. All right, so what am I going to do with that? So I'm going to do this integral with substitution. And when I say that, I don't mean the method of substitution when I integrate. I mean finding the Taylor series with the method of substitution. So what I'm going to do is I see this thing, and this is a lot like this thing. And so I'm going to turn it into that. And so this is going to be equal to then the integral, and I need to get a minus down here, and I need to get a 1 on the 2, right? So I don't know which one you want to do first. It really doesn't matter. I guess I'll get this 1 down here. So let's get rid of that 2. So the way you get rid of that 2 is you just factor it out. So I'll take out a 2, and that'll be a 1 plus x over 2, and then dx. And I can clean it up even more. Let me move this over. The integral, and I can move that 1/2 and write as 1/2 1 over 1 plus x over 2. And I can even move that 1/2 out. I might move that out in the next step, dx. So I just want to make it clear, like what I'm attempting to do. Everything has a plan. It's like, okay, I'm going to make it look like this guy. And now I got to get rid of that plus. So how do I get rid of that plus? I'm going to move that 1/2 out. The integral of 1 over 1 minus, and in parentheses, all right, negative x over 2. And that'll do it. It's got the right type, right? So it's like, hey, there's your triangle. Whatever it is, you replace it with it. So there's it. And so this should be equal to then, we have the 1/2 on the outside, the integral of this infinite sum, so sum n equals 0 to infinity. And then for this x, I plug in this negative x over 2. So in parentheses, I have negative x over 2 to the n dx, and that's 4 negative x over 2. And again, if you want to keep the parentheses on there, you can, but you can drop them off in that case, is an element of negative 1 to 1. So I'm going to stop there for a second. So you just kind of look at that. Make that a nice looking x. All right, so this one incorporates substitution into the method using integration. So it's kind of a nice problem because, you know, don't have to test you on substitution, because if it tests you on this, it's like, boom, substitution's automatically involved in it. All right, so what's next? And so here you want to show your work, and a lot of people not show their work on how to take derivatives or integrate this stuff. So it's kind of important that we show our work. So this is going to be 1/2 the integral, the sum n equals 0 to infinity. So before I flip flop the integral and sum, I'll probably rewrite this as negative 1 to the n times x to the n over 2 to the n dx. All right, so I just take that nth power through. The negative becomes negative 1 to the n. The x is x to the n. The 2 is 2 to the n. And now, if you want, I can flip-flop the sum and the integral because it's really ready to go. All right, so here I have 1/2. So the integral of the sum is the sum, so the sum from n equals 0 to infinity of the integrals. So the integral of negative 1 to the n times x to the n divided by 2 to the n dx. And if I want to be really good about this, I could just pull out all the stuff that is constant and just leave the stuff that's being integrated left over. So this is really equal to 1/2 the sum n equals 0 to infinity. So you just can see that -1 to the n doesn't really matter on the integral because it's a constant. The 2 to the n doesn't matter because it's a constant. And then we have the integral of x to the n dx. And so then this is going to be equal to, I'm going to integrate this thing now. So remember, when you integrate, you add 1 to it and divide by it. So I'm going to get basically, and I'm going to put this 1/2 back inside here because we don't need it on the outside. So n equals 0 to infinity, -1 to the n, divided by 2 to the n plus 1, because you multiplied 2 to the n times 2, so the exponents add. There's a 1 right here, right? And then the integral, so what's this integral? You just add 1 to it and divide by it. So x to the n plus 1 divided by n plus 1. And then don't forget the plus c on the outside. All right. So we're looking good. Yeah, we're looking good. Okay, so this has a couple extra steps to it. First of all, we have to figure out what c is. All right, so to figure out c, let me zoom out a little bit. So you kind of pull it up on the screen here. All right, so to figure out c, we know the actual function. The actual function is ln of 2 plus x. So we know what? F of 0 is equal to ln of 2. You just plug it in up here. So that implies that if we plug in 0 here, right? So what happens when you plug in 0? We can write it out so you can see. So I have the sum n equals 0 to infinity of -1 to the n over 2 to the n plus 1. And then we put a 0 to the n plus 1. Make that better. Divided by n plus 1 and plus c. And this is supposed to be equal to that ln of 2. Now notice, because you start this at 0, and this is n plus 1, this is going to be 0. And so it tells you immediately what c has to be equal to. C has to equal ln of 2. And so what do we get? We get ln, or f of x here, equal to ln of x 2 plus x. Is just equal to the sum n equals 0 to infinity. And we'll write this as -1 to the n, all divided by, we have 2 to the n plus 1. And then I'll put that n plus 1 down here. And then times x to the n plus 1. So that's what we know so far. Oh, plus, and then don't forget, I just found this out, right? Plus ln of 2. So we have to find that constant of integration. And so this one turns out not to be 0. The last one we did, I think, in class was 0. So it doesn't turn out always to be 0. Then be careful, because on integration, don't forget, you must test the end points. Because when you integrate, we talked a little bit about how it makes a function, you integrate a function, it doesn't make it worse, it actually makes it better in a way. So how do we test the endpoints? Well, first we have to remember where this thing is defined for. So we up here, we kind of left that alone. So we need to fix that. So this is 4. For what? Well, this implies that -x is between -2 and 2. So we multiply everything by 2, basically. And if you multiply by a negative, it just flip-flops it. So that implies x is still between -2 and 2. So down here, this is good for x between -2 and 2. And so now we need to test what happens when you plug in -2 versus when you plug in 2. So let's do that. We're going to plug this in right here. And you really don't care about the ln of +2. that doesn't matter. ln of 2 is a number, so I would just plug it into the series. You don't have to plug it into the whole thing. So when x equals -2, this implies what? So you have the sum, it equals 0 to infinity of -1 to the n. I'm just copying down up here what I have, and then 2 to the n plus 1, all times n plus 1 at the bottom. And I'm plugging in -2, so I have -2 to the n plus 1. And now I'm going to work with this algebraically to see what happens. So sum n equals 0 to infinity, -1 to the n over 2 to the n plus 1 times n plus 1 all on the bottom. And then how do we separate this? Well, this is going to alternate. So it's going to be like -1 to the n plus 1 times a 2 to the n plus 1. So remember, -2 to the n plus 1, we can just rewrite that as being the same thing as -1 times 2, all raised to the n plus 1. And then we give the n plus 1 here and here because it's an exponent. All right. So what the heck does that do? So let's see. I see the 2 n plus 1s are going to go away. That's nice. And equal to the sum n equals 0 to infinity. And then what is this trying to communicate to me? Well, I add exponents here. So I get -1 to the n plus 1, which is 2n plus 1. Oh, that's communicating something to me. Because what type of power is 2n plus 1? It's an odd power always, right? So if you take a number, multiply by 2, it's always even. So if you add 1 to it, you always get an odd power. And so that's going to be equal to the sum, it equals 0 to infinity of just -1 over n plus 1. And this is a homework problem, right? And so I would say this one diverges. So diverges by the limit comparison test. We're out of room here. By limit comparison test. And I'd compare it with the sum of 1 over n. Even though it's negative, guys, it's all negative, so you just make it positive because it's all negative, right? And so it's basically like a p series with p equal 1. And some of you guys said that, like, oh, this is like a p series with p equal to 1. Well, it's not really a p series. But if you re-index it, it would be, right? So if you re-index it, it would be a p series. A p series, remember, does look like the sum of 1 over n to the p. I mean, that is a p series. So if you put n plus 1 or n minus 1 down there, technically it's not a p series. I don't think I would take off really much for that, but you really would probably use a limit comparison test with the sum of 1 over n on it. Okay. So what does that mean? That means we don't include -2, but we still have +2. So let's see what happens when x equals +2. So when x equals +2, what's going to happen? So again, we're going to come back up here, and we're just going to plug it into the series part because a plus ln of 2 doesn't really do anything for the convergence. So it's n equals 0 to infinity, -1 to the n, divided by 2 to the n plus 1, and then times an n plus 1. And now we have 2 to the n plus 1. Right, so we're just plugging in 2 in for x. Oh, I like that. That's going to go away real fast. And so I just get the sum, n equals 0 to infinity of -1 to the n divided by an n plus 1. And this is going to converge. This converges by the alternating series test. Therefore, we can do our final statement. These are long problems. Right, whenever you use that integration, lots of steps. Therefore, what? ln of 2 plus x is actually equal to this infinite sum, n equals 0 to infinity, -1 to the n, divided by 2 to the n plus 1, make that n better. And then there's the times n plus 1 on the bottom, and then an x to the n plus 1 on top, plus ln of 2. Oh, my bad. Don't forget to say when, because that's a big deal here, right? So let's take that out. For x between, we saw we don't include -2, so parenthesis on -2, but we do include 2, so square bracket on 2. And every once in a while, a student will tell me, well, shouldn't we write that as just somehow as x to the n and not n plus 1? Shouldn't we re-index it? I'm like, well, if you really want to re-index it, you can. But if you get this far, I'm like, that's awesome. That's a lot. There's a lot of steps there, a lot of things to to remember. So if you can just get down there, I think you did a great job and you're ready to kind of move on. Re-indexing is not that big of a deal at the end of the day. Okay. So let's pull that up. Maybe let's step back just one step so we can pull it up all on the same screen maybe and have it up there. So if people that want to later pause the video can. So there it is, and it's all its glory, right? I should check to make sure it's solid. Yeah, it's good. All right, so that's C. We have one more painful one and then one that's going to go real fast. Okay, so let's do the last sort of painful one, which is using the definition. So let me come back here, get all sort of centered. All right. So we did A, B, C, and now it's time for D. So on D, what did we have? F of x equals cosine of x. And we did this one actually in class, but it doesn't hurt to look at it again and try to attack it like for the first time. So when you ask me to use a definition, I know at the front of the exam, or in this case, the final or whatever, or in the front of the exam here, I have this information. And the definition, what we mean by the definition is use this thing right here. So I copy that down. So I would copy down the Taylor series T of x is equal to the sum, n equals 0 to infinity, of the nth derivative of f evaluated at a divided by n factorial times x minus a to the nth power. So I copy it down. And that tells me what to do, right? So that's the first step. So I'm like, okay, I know this is centered at A. And so in fact, I might even go back up and be like, okay, I can center this at 0, right? So remember, it's centered at 0. So I might go back up here and just plug in the 0 to begin with, because that makes life easy too. So x to the n. Perfect. Oh, and now I'm even happier. The A always bothers me. So now that I use that definition, I'm gonna just move it off my screen here a little bit. So I'm gonna get it out of here. So now I have that definition, what I'm gonna do is just find those derivatives and plug in 0, because I'm looking for the formula. That's what I really want. I want the formula for this thing. And so here, let's make a table. So make a table over here. I have n, and I do 0, 1, 2, 3, 4, and as many as I need. And then I have the nth derivative of the function, as many as I need, again. And then over here, I plug in 0. So the nth derivative when you plug in 0. And the first one's easy, right? The first one is just a function. So cosine of x. And I take its derivative. So cosine is negative, so negative sine of x. And then I take its derivative, so negative cosine of x. And the next one is going to be negative and negative, because cosine is negative sine. So negative negative is going to be sine of x. And then cosine of x. And I might do a couple more here just to get a feel, right, for what's happening. So cosine is negative sine of x. And I just keep on going until I feel like I might be okay. Right. So then negative, oh, okay. So I see a pattern, right? And so what's going to happen? I'm going to plug in 0 now. And so over here, I'm going to show you what I'm doing. Cosine of 0 is equal to 1. Negative sine of 0 is equal to 0. Negative cosine of 0 is equal to negative 1. And now I kind of get it. Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine is negative 1. So I see what's kind of happening. The problem, though, is what? So when we did this in class, it's really hard to find the pattern here, guys. So ... when you plug in, it's like, what is the pattern? And it turns out you can't do it. Because of the way it goes 1, 0, negative 1, 0, 1, 0, negative 1, you'd actually have to probably define it piecewise. If this, then you do that. If this, you do that, basically. So you probably can't actually define it as a table's written. But if you write out the first couple terms, you can rewrite the sum just from the pattern that you see. So what you want to do here is just write this out. So you want to find f of 0, and you want to do f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared plus, and do the third derivative, and so on and so forth, right? So that's what you're really trying to do. So, I mean, this problem is really nice because of that. And that's why it's a great problem for us to do in class, to kind of show you it doesn't always work. You got to kind of, just push ahead, do what the formula says. So notice, how do you do this? Well, we know what f of 0 is. It's 1. So it goes 1 plus, and then this turns out to be 0 because the next one's 0. So plus 0 times x. And then it turns out to be minus, and we know what this number is, minus 1. So it's minus 1 over 2 factorial x squared plus the third one is 0. Oh, so 0 times x cubed. I don't even care about the factorial, put 0 there. And then the next one, right? So what do we do all this? So we did 1, 0, and then it goes 1. And so it's going to be plus 1 over 4 factorial x to the 4th. And then it's going to be plus 0. So you just keep going. 0 times x to the 5th. And then it's minus. So minus 1 over 6 factorial x to the 6th plus ... And now I'm going to clean it up because all these zeros I'm just going to throw out. And the pattern will basically emerge. So it's equal to 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th. And as soon as I write that next term here, I'm almost positive it should be minus 1 over 6 factorial x to the 6th, which it is. I bet you the next one will be 1 over 8 factorial x to the 8th. And now I got it. And minus ... It goes on in that pattern forever and ever and ever. And so now, when I go to write down the formula, this will equal the sum, n equals 0 to infinity, I think. It's going to alternate, so we'll do negative 1 to the n. Make sure it alternates right. So when you plug in 0, you do get out 1. When you plug in 1, you get out negative 1, and so on and so forth. And now I got to figure out, I always have a 1 on top. So if you want, I can write this as 1 divided by, and here's where you have to be careful, right? Because I can't put n factorial because it's not n factorial. It's always even. So it's actually 2n. And make sure you put parentheses around it, factorial. And it's x to the, it's always even. So it's not n, it's 2n. And that's an 8 right there. So it's 2n. And that's it. All right, so that's the answer. Right, for the Taylor series representation. But then we have to figure out when it's equal to that, right? So I can rewrite this if you want, 0 to infinity, negative 1 to the n over 2n factorial, x to the n, x to the 2n. And now I got to figure out when it's equal to that. So this is what makes the definition doubly hard. One, you have to derive the actual Taylor series from the very beginning. Then you got to figure out when does it converge. So down here, we have to run a ratio test. So we have to do a ratio test on this thing. So we found its power series representation, which we call the Taylor series. Now I got to figure out when it converges. So we need our a sub n. So our a sub n here is just this term. So let's just write it down. So it's -1 to the n over 2n factorial x to the 2n. And so we're going to run this. That's the limit as n goes to infinity. And then ratio test says absolute value, a sub n plus 1 divided by a sub n. And so that's going to be equal to the limit as n goes to infinity. And now we just do what it says. So wherever we see an n, we're going to write n plus 1. And we'll put it in parentheses just to kind of help us. So up here, wherever you see an n, write n plus 1 in parentheses. So -1 to the n plus 1. And again, we'll just, for fun, we'll put in parentheses. And then x to the 2, and in parentheses, we'll write n plus 1. And then on bottom, we have 2n factorial. So we write 2 in parentheses and n plus 1 in parentheses factorial. And so that's a sub n plus 1. And then divided by a sub n, which again, you just copy that down. That's nice and easy. So -1 to the nth power, x to the 2n, divided by 2n factorial. And then don't forget, that is all absolute valued. So now on this one, to speed it up a bit, let me remind you, because a lot of times you guys try to work with these absolute values. I'm like, no. These -1s, these just go away because you have absolute value. Remember, -1 to the n, what does it do to an expression? It makes it positive or negative. That's it. So when you slap an absolute value on there, guys, you just can drop it off because this is multiplying by plus or minus 1. So I'll just take that off to make life easy on me. And then rewrite this as the limit as n goes to infinity. And I'll start simplifying this. So, this x to the 2n plus 1 is really x to the, that's a 2n plus 2. So it's really an x to the 2n times an x squared. And I'm doing that because I know there's something down here to cancel with. On bottom here, I'm going to be a little bit careful. So I'm going to do this in maybe two steps. So I'd probably write this as 2n plus 2 factorial. Because again, 2 times n plus 1 is 2n plus 2. And then times, I'll multiply by the reciprocal here. So 2n in parentheses factorial divided by x to the 2n. And then don't forget the absolute value. And then you see the things that are starting to cancel here. That cancels with that. And there's going to be some cancellation here, but we'll do one more step just to make it very clear what's canceling. And so on top, we have x squared times 2n factorial. And on bottom, I have this thing. So let's write out what that is. That's 2n plus 2 times, take away 1, so it's 2n plus 1, times, take away 1, so it's 2n, and you keep on going, so it's 2n factorial afterwards. And again, that's absolute valued. And so you can kind of see how it really cancels here. So the 2n factorials are going to cancel. And so this is going to be equal to the limit as n goes to infinity, and its absolute value of x squared. We'll keep the absolute values on there, although you don't have to because you're squaring x. And then on top, you just have a 1. And on bottom, we have this 2n plus 2 times a 2n plus 1. And hopefully, you see now, as you go to infinity, what happens here? This is going to be equal to 0 times absolute value of x squared, which is always equal to 0. So therefore, right, which is always less than 1. So that's always less than 1. So therefore, what? So therefore, how do we want to write this? So therefore, did I give this a name up here? T of x, yep. So therefore, let's write T of x. So therefore, T of x converges for all x, which implies r is equal to infinity by the ratio test. Therefore, let me zoom out here so we can see the whole picture. So therefore, our very final statement, we want to say that cosine of x is actually equal to this sum, n equals 0 to infinity, of -1 to the n over 2n in parentheses factorial x to the 2n for x between, and since it's infinity, it goes -infinity to infinity. All right, so remember, this is centered. So we find this thing centered at 0, basically. And then we find out our r, right, our plus r and our minus r are basically plus infinity and minus infinity. So it goes all over, right? The whole thing. Boom, all the way out. And so there's our concluding statement. That's good. And again, hopefully you feel the pain. Like it's like, oh, binomial theorem, ouch. Oh, definition, ouch. So, strategies on the exam, if you have to use a binomial theorem, you may be like, well, I think I'll do some of the other problems first and come back if you feel like you're, getting low on time and stuff, because you can spend some time on the binomial theorem and on the definition, right? So you might want to knock out the ones you're like, I can get those pretty fast because differentiation goes pretty fast. Direct substitution goes pretty fast. The other ones, though, can take a little bit of time for you. All right, we have one last one to do, which is differentiation. So that's part E. So let's copy that one down. So part E, let's use black here. And what is it? So this is the same one from the homework, guys. So f of x equals 2x divided by 1 minus x squared, quantity squared. And so I just look at that thing and I'm like, oh, you're good, because 2x, that 2x on top bothered some people, but I'm like, that's a great thing to have because that's a derivative of the inside. So I'm like, I'm almost positive this is going to be d dx of 1 over 1 minus x squared. The only thing I'm not sure about is if it's off by a constant or not. So I just need to check that. So on the side over here, on the side right here, I'll write down what is 1 minus x squared to the -1. When I take a derivative of that, I get -1 times 1 minus x squared to the -2. That's the derivative of the outside. And then times the derivative of the inside, which is -2x. And so that is equal to, the negatives are going to cancel. I have a 2x on top over a 1 minus x squared, quantity squared on the bottom. Check. I don't have to deal with the negatives. I don't have to deal with the 2. It's all there. All right, so it's kind of nice. If for some reason we put the number 6 right here, you're going to have to put a 3 right there. Because if you don't put a 3 right there, it's not going to line up right. Right? That'll be 3. Then 3 times 2 will be a 6. So think about that for a second, because it is a guess and check. I would guess 1, and then I realize I got to put a 3 there, and I'll change it a little bit. You guys see that? All right, so let me get that off of there because that's not really part of this problem. Okay, so now what do I want to do? Oh, I'm like, this is substitution all day long now. So over here, let me pull this up again. These are the formulas that I'm given. So you probably should have this memorized by now, but if for some reason you didn't, you could always use it. And so now I'm just going to use that formula there. And it's already in the right form, guys. Like it's already 1 over 1 minus something. So this is going to equal d dx of, and I write the sum, n equals 0 to infinity. And then instead of x, I have x squared. So in parentheses, if you want, I can write x squared to the n. And then this is going to be 4 x squared. If you want, I can put parentheses around that. It doesn't really matter. An element of -1 to 1. So notice, just plugging in, if you want a good rule, if you struggle with substitution, substituting things and for other things, functions aside functions, basically, composition, just put parentheses around it, and then it tells you what to do. And so this is equal to, before I take the derivative, I can rewrite this as the sum n equals 0 to infinity of x to the 2n, and that's 4. And then remember, x squared is between -1 and 1. It's always -1 and 1. So what happens is when you square root this interval, when you look for what interval, when you square it, you get -1, 1, you'll see that x is between just -1 and 1. Right? So it's kind of nice, and yeah, it makes life easy that way, right? All right. And so now we have a few more steps here. We got to flip-flop the derivative sum sign, right? So the derivative sum is a sum of the derivatives. So sum of n equals 0 to infinity of d dx, x to the 2n. And so that's equal to then the sum n equals 0 to infinity. And now we'll just take the derivatives. So how do you take a derivative? The power comes down and you get x to the power minus 1. So 2n minus 1. And so then this is equal to, and now notice n is equal to 0 here. That's actually, you actually don't need that, right? Because if n is 0, that's actually 0. So I probably would restart this, just start at 1, because I don't need the 0 information. And then 2n, x to the 2n minus 1. And then that's 4 x between -1 and 1. And you do not need to test the endpoints because you're doing differentiation, which basically makes things worse at the endpoint. If you included the endpoint in the beginning, you do need to test it in the end, but we don't do those types of problems. So you don't need to necessarily worry about it. Okay, and that's it. All right, guys. So that is the review for exam 4. I am going to stop the video here.